Hello again. Today we're going to talk about carboxylic acids and derivatives of carboxylic acids. And there is quite a number of functional groups that we have to look into. Six of them, as you can see from the title screen. So first, let's talk about how these functional groups look like and what they have in common with each other. So the first one, of course, is the carboxylic acid functional group, which you have seen in the past. You have your carbonyl CO double bonds, and attached to that you have your OH, right? And that's what makes this a carboxylic acid. Um, a derivative of that, which you could consider being the condensation of two carboxylic acids together, and you wouldn't be mistaken to think of it that way, are the acid anhydrides, which, as you can kind of see, it's a carboxylic acid on the left side, a carboxylic acid on the right side, except that the OH is no longer there. You kind of lose that in the process of making the acid anhydride. And the name kind of tells you that that's more or less happening because if you think about it, two carboxylic acids are meant to have a total of four oxygens, right? But here you only have three. And not only that, but you've lost the two hydrogens that would be attached to the second oxygen. So in essence, you have lost a water molecule. And that's why this is called an anhydride, because you no longer have that water equivalent. We also will talk about the acid chlorides, which are directly made from the carboxylic acids using thionyl chloride. Esters, of course, will play a role in our discussion within this unit. The same thing goes for amides and even nitriles, which you may or may not have talked about in the past. Now, all of them, as you can see, have the carbonyl carbon, with the exception of the nitrile, right? But the one thing that you should notice is that for the carbonyl carbon, there's always three connections to three elements more electronegative than carbon itself, right? So like three connections to oxygen, or two connections to oxygen, one to chlorine, two connections to oxygen, one to nitrogen, or three connections directly to nitrogen. And what this ultimately means is that each of those carbons is oxidized all the way to the 3 plus level. And this is almost the highest oxidation you can have on carbon, the highest being 4 plus. So these guys are basically one electron removed from being the most oxidized versions of the molecules. And what you'll see is that as a result of that, many of these molecules, like polyamides, polyesters, tend to be used in clothing that is claimed to be resistant to catching on fire because they're already almost at the highest oxidation state, so they don't have like a huge incentive to like undergo the burning process. But if you force it, they will. Okay, so what this will lead us into is the naming of all these molecules. Um, we're going to start with the carboxylic acids, and then we'll make our way down all the way to the nitriles. And incidentally, I'm doing this exactly in the order of functional group priority. So we're going to start with the highest priority, which is the carboxylic acid. After that, acid anhydrides take priority. After them, esters, then acid chlorides, then amides, then nitriles. And to some degree, the priority is definitely arranged based on how much oxidation is happening at that central carbon. The more electronegative the element to which it's bound, the higher the oxidation state is going to be, right? So that's why carboxylic acids, anhydrides, and esters are above in priority than the acid chlorides or even the amides, right? Because chlorine and nitrogen are not going to be as electronegative as oxygen. So they take lowest priority. And then by the same logic, the nitriles take the lowest priority out of all of this because nitrogen, it's never going to compete with even one connection to oxygen. So it takes the lowest priority. And unless all you have is a nitrile group and just regular substituents, the nitrile group usually doesn't even get accounted as a functional group. It can be treated as a substituent if other higher priority groups are present. So that would be something to keep in mind. Okay, so let's start by naming some carboxylic acids. The way you do this is you find the chain that is longest in your molecule, and you name it as if it were just a regular alkane. And after you do that, the last E of that alkane name is dropped. And in its place, you use the suffix oic acid. And this is going to be true for all the carboxylic acids, as far as the IUPAC nomenclature, is concerned. So for instance, if you look at the molecule right here, the longest chain happens to be 4 carbons long in total. And what you can see is that you have 1 and 2 methyls sticking out of the chain at positions 2 and 3, right? Because we want the functional group to have the lowest number since it's the highest priority in everything present in this molecule. So the name of this thing will be 2,3 butane if you name it as an alkane, right? But now acknowledging that it's got the carboxylic acid functionality, we drop the letter E at the end of the name and we replace it with oic acid, right? So the name is 2,3-dimethyl butanoic acid. Okay, now let me give another example. If you look at the molecule right here and trying to choose the longest chain that incorporates all the functional groups present, you'll find out that starting from the carboxylic acid, the longest chain ought to take this trajectory, which will incorporate not only the carboxylic acid but the alkene and even the alcohol in the entire segment. So if you count this, you have 1, 2, 3, 4, 5, 6 carbons, right? So we have a hexane derivative. What's sticking out of the hexane derivative is once again 2 methyls at positions 2 and 3. But then we have the alcohol sticking out at position 5. And because the alcohol has a much lower priority than the carboxylic acid, we can actually refer to as the alcohol as if it were a substituent. One of the rare cases when we do that. But now in second half of organic chemistry, it's going to be more common than you would have thought originally. So as far as the name goes, right, we would say that this is 2,3-dimethyl hexane, right? Then we acknowledge that, okay, the alcohol is lower priority, much lower priority than the carboxylic acid, and it's a position 5, so we can just name it as a substituent. Specifically, we can call it just hydroxy. So we'll place that at the very beginning because H takes priority, alphabetically speaking, over M of methyl. All right, and then at that point we deal with the alkene and the carboxylic acid, right? And then the carboxylic acid is at position 1 because that's the highest priority. The alkene happens to be at position 2, 3, so it starts at position 3. So you will say that this is, an ene at position 3, a oic acid at position 1, right? And to acknowledge for all of those functional groups present, you basically just dropped the ane ending. And then you say, okay, so this is 5-hydroxy, 2,3-dimethyl, hex 3-ene, 1 oic acid. And that will take care of all the functional groups and substituents present in that chain. Now, if you want to be thorough about this, you could also take note of the fact that the alkene is in the trans position. So you could say that this is the E version of the alkene, just to account for everything in here. All right. Now, if it happens to be the case that you are dealing with a cyclic molecule and that is the parent compound, then the carboxylic acid will have no choice but to be attached outside of the ring. So what you will do is name that cycloalkane as you normally would in any traditional problem. But then what you would do is you will add the suffix carboxylic acid, like literally the entire name, carboxylic acid as a suffix, to emphasize the idea that there is a CO2H fragment sticking out of the ring. Kind of like this, right? So if you look at this thing, the parent chain is a cyclopentane ring, but we have 2 carboxylic acid units sticking out of the ring. And you still want to give those positions on the ring the lowest number possible to favor the functional group, the carboxylic acid functional group. So this will be position 1, that will be position 2. And so we will say, yes, this is cyclopentane, but we have the carboxylic acids, 2 of them, at positions 1 and 2. So this ought to be called cyclopentane 1,2 dicarboxylic acid, right? And you have to include the prefix di, because if you don't, you will be telling the reader that there's only one carboxylic acid, even though you're putting the two numbers in there, right? So it'll become pretty ambiguous as to what's happening. So you got to be pretty consistent with this. Okay, now another example of that, using the bicycloalkane right here, and noticing that we have the carboxylic acid sticking out of it, we have to acknowledge that yes, this is bicyclo, and then if you count the carbons, right, we have 1, 2, 3, 4, 5 in total in there, so it's bicyclopentane. And if you count from the bridgeheads, how many carbons we have to the left, we have 2. How many carbons we have to the right, we have 1. How many in between the bridgeheads, 0. So you have the bicyclo 2.1.0 denomination, pentane, right? We already know that has 5 carbons in total. And then the carboxylic acid sticking out of the chain. Now, here you have to be careful because the numbering, although we're trying to give the carboxylic acid the lowest number possible, the rule for bicycloalkanes is that the bridgeheads, one of the bridgeheads is going to be position 1 from the get-go, right? So unless the carboxylic acid moiety is bound to the bridgehead, then, you will have a different number for it. And in this case, it happens to be at position 2, right? Because if this is bridgehead, position 1, then that will have to be position 2. And that's the best you can do in this molecule. Okay, now to kind of finalize the carboxylic acid naming, we're going to talk about some of the common names that you should be aware of. And I'll apologize in advance because, as you're about to see, there's quite a bit of them. First of all, the one carbon carboxylic acid derivative is known as formic acid. This is the acid that ants produce in their bodies, and this is a carboxylic acid that's toxic to us humans. So we don't eat ants, and for that matter, we don't eat anteaters because that's their main source of food, and so they have a lot of formic acid in their system. So if you ever wonder about that, yeah, that's the main reason we don't even touch or think about consuming anteaters. All right, and the next one, which is one more carbon long, acetic acid. This is the main constituent that you associate with vinegar. Now, granted, most of the vinegar that you would buy at a grocery store is probably very dilute, like 4% acetic acid at best. Because if it gets much higher concentrations, then not to say that you cannot tolerate the smell, but it is a lot more. It's stronger. It's definitely stronger and a little bit intrusive. All right, now 3 carbons long. This is known as propionic acid, and yes, propionic acid versus propanoic acid, it's almost the same thing. So even I am kind of like, who came up with this name? Like it's like, okay, well, what was the point? But it is what it is, right? So another one that I might mention from time to time, which is 3 carbons long, but does include a hydroxy substituent, position 2, is lactic acid. Now this one pains me to include here, mostly because I am lactose intolerant, right? So this one definitely pains me for reals. So, but we might talk about it. Now, 4 carbon longs without any substituents, this is known as butyric acid. And, between butyric acid and butanoic acid, not a whole lot of difference. A little bit more than propanoic acid, but not by much. All right, now here's where things start getting kind of interesting because now we start getting some pretty unique names. When you have 2 carboxylic acid units directly connected to each other, this is known as oxalic acid. And this particular molecule is one of the main components of the citric acid cycle, if you guys have taken biology. Then we have another one that actually separates the 2 carboxylic acid moieties from each other by one CH2 linker, one methylene linker. This is known as malonic acid. And we will be talking about malonic acid chemistry in more detail in the upcoming lectures. So this will be definitely one to absolutely remember by structure, by name, through and through. Increase that carbon chain by one more methylene linker. This is known as succinic acid. And if you go one more methylene linker in length, you get to glutaric acid. All right, now going kind of back to succinic acid, right? If you go from having an aliphatic chain in between the carboxylic acids to one that's basically an alkene, you have 2 options. One where the alkene is trans, in which case this is known as fumaric acid, or one in which is cis. And in that circumstance, you're dealing with maleic acid. Now, here you kind of want to be careful because um, it's very easy to confuse the names of maleic acid and malonic acid with each other, but their structures are very different. And also the restraints in where the groups are pointing and what they can do is very different. So you got to be sure not to confuse maleic acid with malonic acid. Okay, now one that we've talked about in the past, which you probably remember, is benzoic acid, basically the carboxylic acid unit attached to the benzene ring. You got yourself benzoic acid. But there's other derivatives where you do have multiple carboxylic acid derivatives attached to the benzene ring, such as this one right here, in which the carboxylic acids are ortho to each other. This is known collectively as phthalic acid. Okay, and notice that there's no consonants for the first four letters, right? Or excuse me, there's no vowels for the first four letters. So phthalic acid sometimes can be a little bit difficult to remember that. Now, if the carboxylic acids are meta in respect to each other, then this is known as isophthalic acid. And if the substituents happen to be para to each other, well, then this is known as terephthalic acid, right? So, different ways of kind of like emphasizing where things are located. So, yes, there is a number of them that you have to remember. In my opinion, acetic acid, formic acid, malonic acid, benzoic acid, and phthalic acid might be probably some of the more important ones. I'll even toss in oxalic acid in there for good measure, because you'll see that in biochem classes in the future. Okay, so with that in mind, we're going to stop right there, and then we'll continue talking about what happens when you deprotonate the carboxylic acid as far as the name is concerned. So I'll catch you in the next video. Bye-bye.